The next example is also a relatively simple problem that you could have gotten in other ways, but here let's take a look at the statement of it. Have a parallel beam of light enters a clear glass bead. The index of diffraction of the bead is 1.4, and its radius is 1 centimeter, and it's in air. It didn't really say here, but since it didn't say, I'll put it in air. And at what point does the bead focus the beam? And for any kind of determining focal length problems, one generally will put the either the input or the output plane on the surface of and the output plane at the focal point. Uh, if it's looking for the secondary focal point, you put it at the front surface and then the output plane at the focal point. If it were you were looking for the primary focal point, you would put the input plane on the primary focal point, and the output plane you would put at the back surface. But here we've got the former. So I put the input plane on just in front of the first front surface. I'm entering with parallel light, and I put my output plane wherever that light is focused, which again I don't know, so I have to put that value as x here from this back of in this case the plastic bead or the glass bead. So again, one does the, the the following is that I have to get from this side over through this curved surface, and that is a refraction matrix. Then I have to translate to the back surface. That's this translation matrix. And then I have to get to the other side of this curved surface. That's this refraction matrix. And then finally have to translate that to the point, a distance x behind it to get to that output plane. So again, I wrote these in reverse order when I wrote them down. I started here, that's to here, to here, to here, and that gets me over to this point. So even though you're building it from left to right, you enter these from right to left. The refraction matrix, if you remember, is 1 here, a 0 here. Those are the easy ones. And then you have minus n2 minus n1 over n2 times the radius of curvature. This first surface has a radius of curvature of 1 centimeter, and it's convex, so it's positive. I have a 1.4 for n2, a 1 for n1, and then this back one is n1 over n2. I then translate by a distance. Well, if the radius is 1 centimeter, I have to translate through a diameter, and so the translation matrix is 1, 2, 1, 1, 2, 0, 1. Then I'm at the front of this back surface, and now I need to get to the other side of it. And again, that's a refraction matrix at a spherical interface. Again, same formula, n2 minus n1 over n2 times r. In this particular case, r is concave, and so that's a minus 1 centimeters. The radius of curvature is 1. N2 is 1. N1 on this side, as I go from this side to this one, is 1.4. And then N2 is 1. So I get N1, which is 1.4 over 1 here. And then finally I have to translate this distance x again with the translation matrix. Well, I then computed all these numbers here. Some of them I left, but particularly for this one, I reduced it to fractions, and I reduced these to fractions as well. And then just multiplied things out. I won't bore you with the details, but you should certainly check this to make sure I didn't mess anything up. But when I multiplied all of these out, I got this, this matrix here. And now then I'm ready to take my condition for where this focal point is. And if you remember, when A is equal to 0, the output plane is at the secondary focal point. And that's exactly what we have here. So one has, there's my matrix element A. So I have to set that equal to 0 to locate it. And I find when I did this that I got 0.748 centimeters, or about 3/4 of a centimeter is my distance x behind the spherical glass bead. Notice when A is equal to 0, here, well, I think that's all that they really asked for on this one is how far back behind. So I won't go into that any further. So we've gotten located really the secondary focal point for this this object here, all from matrix.